So answer to today's quiz is pretty straightforward. You just had to remember the rules. So the junction rule says that the sum of all currents entering the junction is equal to 0. You could also say it that the sum of currents entering the junction must be equal to the sum of currents leaving the junction. Loop rule says that if we take a sequence of points along a circuit in such a way that the first point and the last point is the same one, then if we add voltages between those points, we will also end up to 0. For practical purposes, when we use loop rule, we just try to find out a certain path, and along this path we add voltages across all elements which we encounter tracing the path. All right. Using Kirchhoffs rules, yesterday we were analyzing a circuit which contains 2 batteries and a resistor, and I asked you to solve the equations. So if we solve the equations, who solve it? Do we have answers? Yes, so we have current I1, I2, and I3. I mean, the best way to do it right now is to learn how to use your calculators, and if you have at least TI-83, it can solve. You just plug in the coefficients in the equation, and the calculator spits out the answers. Anybody has found the current? Yes. I1 was -2. Then it means that it was marked different way. All right, so -2 amperes. I2 was 0 amperes. And I3 positive 2. Then positive 2 amperes, which means that actually this is inconsistent. So I think that this had to be that way. I2, all right. All right, so let's now analyze these answers, because these answers would correspond really to these arrows. I solved that problem too, so I remember how the currents flow, and consistently we had to have it that way, unless Madhumira made a mistake. So let's take a look at this one. If we got -2 amperes, it means that this current has a value of -2 amperes, which means that the conventional current really flows this way, and it has a value of 2 amperes. Not that one. This is I3. We got that I2 is 0, which means that there is no current flowing in this battery. Do you remember that when we didn't have a resistor over here, current was flowing in that battery, and potential difference across each battery was 11 volts. Now when I put this resistor, current stopped flowing. Yeah? So previously it was forced, the stronger battery was forced current in the direction opposite to this, how the second battery would supply current, because normally a battery is trying to push current that way. If I even lower this, the resistance of this resistor, I can get a situation that both battery will start to provide current that way. All right, now I3 is 2 amperes, means that it flows in the direction consistent with this what we marked. Now let's see, just to make sure that we found the values properly, let's separately calculate what is the potential difference between these 2 points, and these 2 points. So in other words, what is the potential difference across this battery, the 10-volt battery, the 12-volt battery, and the connected load resistor? All right, so here, let's call this side plus and this side minus. All right, so V plus minus V minus. If I consider the battery, this battery, I should take electromotive force and subtract product of current and internal resistance of the battery. So I'm going to get 10 volts. Let's now take a look at this battery. So it's V plus minus V minus. Electromotive force of this battery is 12 volts minus, and I have wrong current over here. I should consider current, when I put minus over here, I should consider current flowing this way, which means that I should put here minus whatever I1 is, minus 2 amps multiplied by 1 ohm, and well, this gives me 2 times 1, that's 2 volts, so it's 10 volts also. Let's now check over here, V plus minus V minus. This time I have a resistor over here and current flowing consistently with this arrow over here. Current flows in this direction. So potential plus is at the tail. So V plus minus V minus is just equal to product of the resistance and this current. So 5 ohms times 2 amperes gives me 10 volts. If at least one of those didn't agree, it means that the solution is incorrect. All right. Now I would like to consider a circuit which contains a resistor and a capacitor. How about if we move this thing up and start all over? So this time I'm going to consider a circuit, and for simplicity, I mean, in the program, at this point, we are supposed to see what will happen if we change the potential really fast and keep it constant. So what we are going to do is we have potential difference produced by the source of electromotive force, which toggles between two values. For simplicity, why don't we take this value and call it epsilon 1 and another value epsilon 2. And then how about if we consider that it drops back to epsilon 1 and then comes back to epsilon 2 and so on. And let's consider a circuit which contains this source. So this source produces so-called square wave voltage, or square wave potential difference. So I would have to draw this type of a graph on the symbol, and I consider that this is potential difference between this point and this point. The plot over here is potential difference really between these 2 points. So in other words, I'm considering really an ideal source of electromotive force. Now I can think that actually I combine it together. I combine internal resistance of the source with a resistor which is connected to that source. Let's say that resistance of this resistor is R, and it is connected to a capacitor. So in the book, actually, there is a section which describes charging and discharging a capacitor, and really this is what the case represents. When potential, I mean, like, if I consider that epsilon 1, and this is what we are going to consider, this 0 volts, and epsilon 2 is 1 volt. So when potential difference is 0, it means that these two ends are connected with a piece of wire. So it is like the circuit contains a loop which contains just a resistor and capacitor. When potential difference is 1 volt, so the source of electromotive force produces 1 volt, and the current flows charging the capacitor. All right. Now, in principle, actually, we don't have to use Kirchhoff rules, but I want to. I mean, I like Kirchhoff, analyze all circuits using Kirchhoff's loops, Kirchhoff's rules. It is really the most efficient way to analyze the circuits. So let's say that I will mark current in this direction, although it's arbitrary, and I have to think about which charge I consider on the capacitor. So I will say that charge on the top plate is Q, charge on the bottom plate then will be automatically minus Q. Now I want to make a certain digression for a moment. Let's think about what happens with the charge on the capacitor when current flows, and how the charge on the capacitor is related to this current. So let's say that I have current flowing over here. What happens with the charge on the capacitor? For simplicity, think that it is always try to think that it's conventional current. It simplifies the analysis. Well, this current, I mean, if I have a certain value, it means that it is a rate at which charge is being transferred through a cross-sectional surface of the wire, right? So let's say that in time dt, charge dq, small q, crosses this surface in time dt. So what will be the value of the current? It's a rate at which current charge is being transferred. So it is dq over dt. Right? How about if we read it? I mean, let's think about how to read it. So, I mean, particularly this expression. In other words, I will repeat the definition of current. Current through a surface is equal to the rate at which charge is being transferred to that surface. This is definition of current. Now, what happens actually with that charge which is transferred to this surface? Well, if I consider another surface, an equal amount has to be transferred, right? Because this part is not being charged. Charge does not accumulate. The only place where charge accumulates are the plates of a capacitor. Well, so I go further and further, and I can figure out actually that the charge which crosses each cross-sectional surface of the wire affects the charge on the plate, right? What happens with the charge of that plate? It increases by a certain value, right? Let's write down by how much it increases. By how much charge on the plate increases when in time dt charge d small q is transferred through the surface. Exactly the same amount. This dq has to be equal to this dq. Change of the charge on the plate, I mean the charge on the plate will increase by the amount of the charge crossing the surface, each of the surface in the wire. Do you see that? So if I divide, I mean this change in charge is equal to the charge crossing the surface. Note that over here I said change in charge. Why did I say change in charge? Because charge of the plate changed. Now I cannot say that this is change in charge. This is charge which was transferred through the surface. But they happen to be equal. So if I divide this change in charge on the capacitor by time, I will get the same value as the current in the circuit. However, now I would read it differently, because now my conclusion is that the current flowing in the circuit or in that wire connected to the capacitor is equal to the rate at which capacitor is being charged. Do you see that? Over here I had the rate at which charge was transferred through a surface, through a cross-sectional surface of the wire. Over here I have a rate at which capacitor is being charged. Now current is equal to the rate at which capacitor is being charged because I made a drawing that way. If I made a drawing different way, if I put minus Q over here and plus over here, over there, then I will get that the current is opposite to the rate at which capacitor is being discharged. No, also charged, actually, however, in the opposite direction. So that relationship, current is equal to the rate at which capacitor is being charged, is valid only if you mark current flowing toward the plate which has charge Q, not minus Q. From minus Q, the same current flows away. All right, so this was just a digression, because I don't need it. And let's use Kirchhoffs' loop rule to determine what kind of current is going to flow in this circuit and what will happen in the circuit. We will find everything about the circuit today. I devoted an entire lecture for it. So we'll find what happens with potential difference across this element, what happens with potential difference across this element, what happens with potential difference across this element. We'll find current flowing in the element, and we will analyze the charge on the capacitor at any instant. This is our task for today. All right, so how about if I consider loop in this direction and I use the same convention as the book does. So when I use loop rule, so I will have, here I will encounter plus first. I will write down electromotive force with plus. Now if I have Q and minus Q, it means that I should take this side with plus and this side with minus. From the potential of the top plate, I have to subtract potential of the bottom plate. Now over here, tail corresponds to plus, head corresponds to minus. So the next term is going to be minus Q over C, because this is how potential difference is related to the charge on the capacitor, potential difference across the capacitor. Note that this is potential difference across the capacitor. And the last term will be minus current multiplied by resistance. I have completed the loop. This should add up to 0. And well, here I have for this circuit, I don't know I mean, I know how potential difference varies, how electromotive force varies, because I have this plot and it toggles. I don't know what is the charge on the capacitor, and I don't know what current flows in the capacitor. But I mean, when I have a circuit, I usually know what is capacitance of the capacitor and the resistance of the resistor. So capacitance, consider that capacitance, resistance, and electromotive force are given. Now we have to solve this equation, therefore, for current and charge. Well, there are too many unknowns. However, current and current in the wire and charge on the capacitor are related, right? Because I mean, when I discuss the digression, current is equal to the rate at which charge varies on the capacitor. All right, now I have one unknown. However, this is not a trivial equation. It's not a linear, what kind of equation I got over here? You will have a separate class really to solve much more complicated equations of this type than the one which we have over here. The equation is referred to as the differential equation. We have derivative of a function in that equation. Here we have a certain function and derivative of this function. We don't have single value for charge. Charge is varying. So charge is a function of time. And in order to solve this equation, I mean, algebraically you are prepared actually to solve it because this is a relatively simple equation. Although the same equation really applies to many other disciplines of science. I remember that one of my former students actually came, and I reminded her about this equation because she came with a problem which was her homework problem, and she was supposed to figure out what happens with the concentration of a certain drug when it is delivered to a body. It follows very similar equation. Also, growth of a population, for example, will have a similar equation. There is a lot of situations, not just a circuit which contains capacitor and a resistor. And by the way, because it contains capacitor and a resistor, it is referred to as an RC circuit. R standing for resistor and C for capacitor. All right. Now, in order to solve this differential equation, I'm going to show you a method which is called solving an equation by separation of variables. Now, the variables over here, things which vary, are charge and time. So we have to manipulate now this equation in such a way that we have charge, which is a function of time, on one side of the equation, and time, which is the independent variable, on the other side. All right, so we can just move these two terms to the right-hand side. So minus r dq over dt is going to be equal to q over c minus epsilon, and I can write now that, well, so here I have q, so I can take, and how about if I, yeah, why don't I actually pull out c from here? So I will take 1 over c in front, and then I will have q and epsilon c. And now I will divide both sides by minus r and multiply by dt and divide by this expression. So I can write down that dq over q minus epsilon c is equal to minus 1 over r c dt. All right. So we have separated variables. We have charge on one side, time on the other side. Now what we have to do is to integrate both sides in corresponding limits. So on the left-hand side I will have, and minus RC is a constant, so I can have it in front of the integral of dt And, well, I will integrate over here from the instant when the electromotive force started at constant value. So like, for example, there's T1 or T2 or T3, one of those. I will write down just Ti. And then the upper limit will be whatever instant happens after that, before the next toggle. So to an arbitrary instant t. On the left-hand side, therefore, I will have dq over q minus epsilon c, and the integral has to correspond to the same values. So I will have, and now variable of integration on the right-hand side is charge. On the, left-hand side. On the right-hand side it was time. On the left-hand side it is charge. So I have to have values of charge over here. Charge corresponding to this instant, I will call it initial charge, and charge at instant t. Now, charge I is a charge on the capacitor at this instant, for this time for this interval, at this instant, for this time interval, and so on. Well, now let's use the first fundamental theorem of calculus to integrate both sides. So, indefinite integral of this function, I mean, if you take a look at the tables, or you can think about even solving by substitution. You can consider that q minus epsilon c is u, and then dq is going to equal to du. So du over u, or indefinite integral of this function, is going to be logarithm, right? So it is indefinite integral is logarithm of the denominator. And we have it from q initial to q of t. Now the right hand side is really trivial because it is just indefinite integral is t. I plug in the two values, so I will have t minus t initial. So over here I have time which passes from the instant of toggle. From here, yeah. So this is t minus ti. Or I can do it from here, t minus ti. Let's plug in the values. So logarithm, we will have logarithm of q of t minus epsilon c divided by q initial minus epsilon c. And on this side I'm going to, well, I will just copy it. How about actually if I move it further? Yeah, so this expression is equal to that, which means, logarithm of this expression, which means that the expression itself is e to this power, e to negative 1 over rc t minus ti. All right, now I will have to use the other whiteboard. So I will move this one up. Now we have to solve for that q. And let me do it faster, okay, because I think that I'm going too slow. So in order to do this, first of all, I will multiply both sides by the denominator, right? So I will have e to minus 1 over rc t minus ti, and have this expression in front, q initial minus electromotive force times capacitance of the capacitor. And now I have to move this term. So, and this will be plus epsilon c, and this is Q of t. What have we found here? Charge on the capacitor. When? At any time, at time t, correct. We found charge on the capacitor at any time t. All right, how about if we try now to plot it on the background of the well, how about, no, let's go, before that, let's find out what is the voltage across the capacitor. Let's find out how the potential difference across the capacitor varies. How to do that? Well, I know capacitance of the capacitor, and I know charge on the capacitor at an arbitrary instant. From knowing charge and capacitance of the capacitor, how do I find the voltage? Well, charge is equal to voltage multiplied by capacitance. So voltage is charge divided by capacitance. So I have to divide this expression by capacitance. So let's do it. If I do it, I will get, from this term, I'm going to get just electromotive force plus, over here I will have initial charge on the capacitor divided by capacitance. So really what am I going to get? Charge by capacitance. Which initial potential difference? Yes, so this is potential difference at the beginning of the interval. So this is when the source was toggled. Minus, and here I will have electromotive force, and I took care of everything. E to negative 1 over RC T minus Ti initial. Let's try now to plot this function on the background of this function over there. So how about if I copy this function here? And why don't we actually think about even numerical values? So for simplicity, I really like number 1, and we all, I think, like number 1. So let's think that capacitance of the capacitor, let's say, is 1 millifarad, and resistance of the resistor is 1 kilo ohm. Yes, a this product over here, RC, is going to be 1. Now, the product has to have a unit of the same whatever is in the numerator, because otherwise we will have really mess with the exponent. We wouldn't know how to raise, for example, e to 1 second. We can only raise e to something which doesn't have a unit. So it is obvious that the expression, that the unit of RC has to be second, and actually it is. You can verify that if we multiply ohm by farad, we will get second. So it has a unit of second. However, in the expression, it is a certain constant. And we call that product the time constant of the RC circuit. And it really says, and we will analyze, what does it say? I can say, it says how fast the capacitor is being charged or discharged. And actually, not only that, it says also how fast the current is going to change, and how fast the voltages are going to change, and so on. All right. So let's say that here we have 0 volts, here we have 1 volt, and let's try to see what happens let's say that this is from 1 to 10 seconds. What happens in this interval with the charge of voltage on the capacitor? So let's start with this. What happens at at that initial instant? So this Ti over here, I will use the reference for time over here. So Ti is 0, and let's figure out what will happen here. So when Ti is 0 and t is 0, I have e to power of 0. How much is e to 0? 1. So this is going to be 1. Now what is the initial voltage on the capacitor at this instant? It's 0. So the voltage on the capacitor over here is 0. So really for this time interval, Vi is 0. So this disappears. Now I have epsilon minus epsilon. It's 0. So voltage on the capacitor, across the capacitor at instant 0 is 0. Now considering that E is approximately 3, think what will happen 1 second later. Yeah, so here we will have e to the power of 1 divided by 1, right? Considering that e is approximately 3, e to negative 1 is how much? 1/3, correct. So this expression becomes 1/3. Now remember that this one is 0, right? So now I have to subtract 1/3 of electromotive force from electromotive force. How much is going to be left? 2/3. Okay, now let me mark 1 second. So this is 5 seconds. So after 1 second, voltage across the capacitor is going to be 2/3 of 1 volt. Think what will happen after 2 seconds. Here I will have E2 minus 2. So it is how much? 1/9. So from electromotive force I have to subtract 1/9 of an electromotive force. Right? Now this is 1/3. So 1/9 is 1/3 higher. Right? So I will have a point over here. And then you can see that the next one will be 1/27, and so on. So the voltage across the capacitor asymptotically approaches this value 1. Look what happens after a long time. So after a long time I have e to a negative large number. It is close to 0. Right now with this being 0, and well, all of it is 0 then. Do you see that? All right, let's now see what will happen in this time interval. Now, what happens in this equation? First of all, electromotive force now drops to value 0. Right? Over here, electromotive force is 0. How about initial voltage across the capacitor? 1 volt, correct. This is what we charged by the end of this interval. So this now is 1 volt, this is 0, and this is 0. Let's plot it versus time. So at this instant here, at 10 seconds. So now Ti is 10 seconds, and T is 10 seconds. So I have e to 0, so it's 1. So really I will be left with the initial voltage on the capacitor. So it coincides with that one. What will happen now after 1 second? I will have e to negative 1, yeah, because I will have 11 seconds minus 10 seconds divided by 1 second. So it will be 1/3. This expression will be 1/3. So I will drop to value of 1/3 of the initial voltage. So after 1 second, we have it here. Well, you can figure out that after 2 seconds I will have it here and so on. Therefore, potential difference across the capacitor is an exponential function of time, which looks like that. Now, how about, let's find out potential difference across, well, how about you do that? I want you now to finish it. Find out what is the current. I will give you the hint for it. Current in the circuit. Recall that current in the circuit is equal to the rate at which capacitor is being charged. So we just have to differentiate this expression. We calculate the derivative of this expression, we will get current flowing in the circuit. So you continue that. Now, how about voltage across the resistor? And it's also at instant t. All of this is at instant t. How can I find voltage across the resistor? I have to multiply this current by resistance of the resistor. And you'll find the expression, and I want you to finish to make a drawing of it. And what I will do tomorrow, I'm going to build a circuit, and we will look for these plots in real life. Thank you very much. See you tomorrow.